Functions of several variables. Functions of several variables are functions that contain two or more independent variables. Functions with two input variables can be visualized on a 2D plane with level curves. These are where points of the same value are joined together on a line. By considering all variables except one to be constant, we can find the partial derivative of the function. This is usually denoted by delta f over delta x or f base x. For example, if f of xy equals x squared plus 3xy plus 4x cubed y squared plus 5y cubed plus 6, delta f over delta x equals 2x plus 3y plus 12x squared y squared, and delta f over delta y equals 3x plus 8x cubed y plus 15y squared. Higher order derivatives can be written as delta f over delta x delta y or f base xy. In the first case, f is differentiated in terms of y first, and then delta f over delta y is differentiated in terms of x. In the second case, f is differentiated in terms of x first, and then f base x is differentiated in terms of y. Using our previous example, f base xy becomes 3 plus 24x squared y. To find the derivative in a specific direction, each component of that direction is multiplied with its respective partial derivative and summed together. For example, the directional derivative at xy in the direction of the unit vector u equals f base x times ux plus f base y times uy. This can be rewritten using dot products. The first vector in the dot product is known as the gradient vector and is comprised of the partial derivatives of each component. Using our example, the dot product would be the vector of 2x plus 3y plus 12x squared y squared and 3x plus 8x cubed y plus 15y squared. To find the direction of a certain gradient, we can use the formula the directional derivative equals the gradient vector cos theta, where theta is the angle formed between the direction and the gradient vector. Keep in mind that the magnitude of the directional derivative that you are looking for must be less than or equal to the magnitude of the gradient vector. Some key points to remember. The maximum value of the derivative at a point is the length of the gradient vector at that point. The gradient is 0 at 90 degrees in both directions from the gradient vector. The minimum value of the derivative at a point is the negative length of the gradient vector at that point. To find the derivative of a function in terms of a secondary variable, the partial derivative of each primary variable must be multiplied by the partial derivative of the secondary variable and summed together. Given small changes in the input variables, the change in the output variable can be approximated with df equals the partial derivative in terms of x times dx plus the partial derivative in terms of y times dy. By dividing both sides of this equation by the original function, we can calculate the relative increment of f, where dx over x and dy over y are the relative increments in the individual variables. To identify and classify extrema, first critical points must be identified. This is done by identifying points where all partial derivatives are 0. By setting the partial derivatives to 0 and solving the resultant system of equations, the points can be identified. The next step is to classify the critical points. First, the discriminant must be calculated using the formula f base xx, f base yy minus f base xy squared. If the discriminant is negative, the point is a saddle point. If the discriminant is positive and f base xx or f base yy is positive, then the point is a local minimum. If the discriminant is positive and f base xx or f base yy is negative, then the point is a local maximum.